Okay, we're starting now. The problem, ice problem part 2, is what mass of 120 degrees Celsius steam is required to melt 1 kilogram of negative 20 degrees Celsius ice so that the equilibrium temperature, the TF of the system, is 0 degrees Celsius liquid. So it would be on the right side of the first plateau in what we would call Q2. So intuitively, you want to ask yourself, what's going to be larger? Is it going to be, you have 1 kilogram of ice, is the steam going to be greater than a kilogram or less than a kilogram? And if so, if not, which one and why? All right, here are the thermodynamic constants for water. Just a very brief overview, and that is that you have to be able to use any single set of thermodynamic constants for water depending on what we're asked to calculate it in. Joules, kilojoules, kilocalories, or calories. So just keep in mind and keep this with you. This is what we're going to be using. Now, this graph tells the entire story. The ice is going from negative 20 ice to 0 liquid. And the steam is going from positive 120 gas to 100 gas. It's going to release the heat of vaporization to 100 liquid, and then it's going to cool from 100 liquid to 0 liquid. Now, intuitively, you want to be able to ask yourself, and I have 2 students with me. I have Gabby and Bree here. Intuitively, and I didn't do this morning with you guys, so you should be able to answer this without any prior knowledge. Intuitively, do you think that the amount of steam, it's 1 kilogram of ice, that the amount of steam is going to be less than 1 kilogram or more than 1 kilogram or equal to 1 kilogram? What do you think it's going to be? So that's what you have to ask yourself. You have to ask yourself initially, you think it's less than 1 kilogram. Yeah. And there's reasons which we will get into that your intuition is excellent. In other words, not just your general intuition, your intuition in physics is excellent. Because you can see just by releasing the heat of vaporization, you're releasing enormous quantities of energy. And if you look back on the graph, these are what's given and the constants. I'll just talk through this. And that is that the ice is going to absorb 80 kilocalories per kilogram. And the steam is going to release 540. That's over 6 times the amount of energy is going to be released from the steam relative to the amount of energy absorbed by the ice to melt. So you don't need that much steam. It's obvious. Now, here's the givens and the initial, the given mass of ice. We're looking for the mass of steam. This is the initial temperatures and then the constants that are listed in your equation sheet, thermodynamic constants for water. Now, a little bit more picture-ish, you'll see that the blue, the steam giving up its energy, it's going to go Q5, and that'll be mass times delta T times the specific heat capacity of gas, and then it's going to give up the heat of vaporization, and then it's going to give up the heat going through the liquid phase, M delta T, specific heat capacity of liquid. The ice is going to go from negative 20 to 0, and then 0 solid, and then from 0 solid to 0 liquid. So you have the ice going through 2 steps and the steam going through 3 steps. Are you with me, guys? Does it make sense? Okay, we're going slowly, so it should make sense. And this is the way I work with all of these problems, Q1, Q2, Q3, Q4, Q5. just remember, if you have your equation sheet out, you'll be able to look back at it because we're about to change the slide. That what we always talk about in terms of Q1, Q2, Q3, Q4, Q5. So the heat gained by the ice will be Q1 and Q2. That's the calculation using those equations. The heat loss will be Q5 plus Q4 plus Q3. And then, so the heat gained will be the Q1 is the mass of the ice times the change in temperature of the ice times the specific heat capacity of the ice plus the product of the mass of the ice, 1 kilogram, times the heat of fusion, which is 80 kilocalories, and then the heat lost by the steam is given in Q5, Q4, Q3. Now, I'm going to put it on, I'm going to stop, and then I'm going to make the next slide a little longer so I have time to go over heat lost. Now, here I have the heat gained side of the equation. This is the ice. Now, look carefully. I have Q1 plus Q2. Now, remember, this is key. You have two separate terms. Each term is made of factors. So Q1 is a term. It's going to be the mass of the ice times the temperature change times the specific heat capacity of the ice, correct? And then plus the mass of the ice times the heat of fusion. Now, the heat of fusion, it's absorbing, so it's going to be a positive heat of fusion, right? Because it's absorbing. It's endothermic. Now, look at what I have here. You ready? 1 kilogram, 0 minus a negative 20, so it's positive, times 0.492. That's Q1, that's one term, that's going to equal 9.84. And then 1 times 80 is 80. And then 9.84 plus 80. So the ice cube needs a total of 89.84 kilocalories. Correct? That's how much it needs. All right? So the question will be, what mass of ice, what mass of steam is going to give me 89.84 kilocalories? That's ultimately what we're getting, right? Okay. So now, we're waiting for the slide to change, but the next slide will be the heat loss slide, heat loss side of the equation. And I will bring the heat lost portion of the formula forward to the top of the next slide, and we'll spend some time on the next slide. Heat lost is Q5, Q4, Q3. The mass of the steam, which we don't know, the change in temperature of the steam, the specific heat capacity of the steam, plus the mass of the steam times the heat of vaporization. And here it's exothermic. It's giving it up. I made it blue, negative, to accentuate that. And then I have the water, the steam turned to water at 100 degrees Celsius, and then it goes to 0 degrees Celsius. So those are the three steps, Q5, 4, and 3. If you look at your equation sheet, you can look and see what those are. So look at the first term, Q5. It's 100 degrees Celsius is the final temperature minus 120 degrees Celsius. You see that? Final minus initial for the steam portion. So it's be 100 minus 120 is a negative 20. If you look at the third line, it says negative 20. The heat of fusion, the heat of vaporization is negative. So that's going to be M times negative 540. And then it's going to go from 100 to 0. So it'll be 0 minus 100, which is negative 100, times 1, which is the specific heat capacity of the water. Okay? So if you look at the first term, that reduces to 9.66. The second term, negative 9.66 M, steam. And then the next term reduces to negative 540 M steam. And then the next term is negative 100 M steam. Add the three terms, you get negative 649.66. I have here with an arrow just to point to the negative, just to accentuate it. The negative sign must be placed here as an interpretation of the physics. The steam is giving up energy. The situation relative to the steam is exothermic. The next slide, I go back to the original equation, and I see that the heat gained by the ice plus the heat lost by the water equals 0. Heat gained by the ice equals negative the heat lost. The heat gained is going to be 89.84 kilocalories. The heat lost is going to be negative 649.66 m steam. So it's going to be 89.84 equals the additive inverse, negative 649.66 m steam. Using the property of symmetry, I'm just flipping it. So divide through, I'm rounding 89.84 to 90. Divide through by 649.66. You get mass of steam is 0.139 kilograms, or 139 grams. And that's the end of our problem. Now, I'm going to propose another problem to you. Let's say everything about this problem is the same except the equilibrium temperature is 50 degrees Celsius. Try that one. The equilibrium temperature is 50 degrees Celsius. Try that one. And we'll look at that the next day in school. So look at this tonight. I'm going to put this up on YouTube. And next week's quizzes will be on the two videos, Ice Problem 1 and Ice Problem 2. Thank you very much, and goodbye.